So let's begin. My name is Meg Krishnaswamy. This is the Data Lab. And today in classical machine learning, we will be discussing recurrent neural networks and their implementations in natural language processing. Rather than the focus being RNNs, I'd like to focus a little bit more on the use case for RNNs and how we would go about processing our data for working with a recurrent neural network and the implementation of a simple neural network for character level predictions. Okay, so let's start with the what. RNNs are primarily used for working with sequential data. So some examples of sequential data: a sentence with say 5 words is a sequence of n is equal to 5. A word which has say 7 characters is a sequence with n is equal to 7. And when the relationships between members of a sequence is important to our research, we want an architecture that looks at each member of a sequence not as an independent event, but as a series of events which have a relationship with each other and are impacted by each other. Right. So for this purpose, RNNs are a popular choice. Another cool thing about them is that they can work with different sequences of varied length. So the length does not have to, the length is a factor which helps provide us with more context for a given sequence. Sometimes it may require more memory or less. It's something that we will look at. Right. Next, as far as the math of coding up a recurrent neural network is concerned, we can think about it as a sequential relation over a given number of time steps. So for a given state, which in this case is S at step K, if we want to determine the state at this point in the series, we use a function that utilizes all the information collected up to the previous state, along with input at the given moment in time and weights that we've generated for the previous step. So we can think of a recurrent neural network as a model which has a loop. And as our sequence continues to add members, we continue to add information to our current state using all the information accrued from previous states, right? So let's look at this graphical representation over here. On the left, we have the input X that's being fed, and for a given sequence or endpoint state S, we see that there is a loop that continues to work on. And if we unfold this loop, we see that there's a series of intermediate states which are going to occur, and there's going to be one intermediate state for every member of the sequence between the first and the last member of the sequence, right? And at every state, we see that a member of the sequence is going to be fed as the input. Okay. Next, what are the possible use cases for RNNs? Now, one, if a task requires a many-to-one or a many-to-many mapping, then that's something that we can use a recurrent neural network for. Now, for example, if we have what we're going to look at today is a character level RNN, where the sequence is a bunch of characters. So for example, if you have the word dog, it has 3 characters, D-O-G, cat has 3 characters, C-A-T, and so on. And the relationship between each character and its neighbor is going to be something that the recurrent neural network is going to learn, and it's going to use this information as in order to predict what sorts of words are allowed in a given context, right? So the network is essentially learning an underlying pattern which that governs which character is allowed next to which in a given language. In a if you want a many to many architecture example, say we have a given name that has a German version and has an English version. Now, logic dictates that there's going to be some kind of relationship or some kind of similarity between the German version of a name and the English version of a name, right? And this is one of the things that's going to give us insight into this relationship between the same version of a word in multiple languages is the relationship between the characters present in the word. And this would be an example where we use a many-to-many architecture for a natural language processing use case. All right, so this is a bare minimal introduction to RNNs. One of the reasons for me keeping things simple is that I'd like to look at all the NLP pipeline steps that will go into today's implementation of an RNN. Also, once we have our introduction to recurrent neural network set, if there's more that you'd like to know, if you'd like to know what the state of the art with with RNNs is concerned, Mithun Paul runs a fantastic workshop, deep learning, on Thursdays. It happens right after this workshop. And there he goes more into transformers architecture, which is part of the lineage that started all the way back from Markov chains with RNNs as one of the intermediate steps. And today we have the GPT architecture that's the most that's currently the state of the art as far as sequence modeling and prediction is concerned. So we'll be looking at just the basic how does all of this come together side of things. And if you'd like to learn more, if you'd like to work at the sentence level, at the language structure level, I invite you to join us on Thursdays for the deep learning workshop, where we cover more modern architecture in more detail. All right. So having said that, I'd like you to click on the notebook that we are using today. So this one, let me add the link in chat real quick. As always, this is a Colab notebook. And if you click on it, it should click on open in Colab. This should redirect you to Google Colab, where we can look at this a little bit more in detail. Okay. Just give me one moment. Okay, so today we'll be working on character level RNNs for classifying names into languages that they are most likely to belong to, right? So in this case, the input is a first name or a last name. The output is one of, I believe, 17 languages that we have data on, and we're going to determine if RNNs are how RNNs would go about processing this NLP task. Okay, now the notebook that I'm using today is from the PyTorch's official website. PyTorch is a Python toolkit for deep learning that was released by Meta, and it's got a fantastic set of documents for most of the processes that you can do with PyTorch. And this I've added to this code to make it more readable and provide more context. And if you'd like to learn more, the link to the original notebook will be available. Right. So first up, what are we using? So we're going to use RNNs, but instead of using it for an advanced NLP task that takes place at the word or sentence level, which RNNs may or may not give us a good computational power, we're going to test our baby RNN today on a character level task, right? Now, a character level RNN in this use case is going to read a word not as a unit of meaning, but as a series of characters, right? It's going to find some relationship between these characters, and it's going to give us a prediction. Now, at every step of the RNN, it's going to create a hidden state. The hidden states will talk more about how these are computed, right? The output of the hidden state will be fed into the next step, and this goes on and on until the sequence has no more characters left, at which point our model will move on to give us a prediction, right? Now, we have a few thousand surnames, and we have 18 languages of origin. And what we're going to do is predict which language a name comes from based on its spelling. All right, so let's start with the data itself. Now, the first box over here should allow you to get the folder that we need for today's workshop. And it should also unzip the file for you. Right now, if this has worked, you should see the list of .txt files. There's one text file for every language. So our names are already in this original data. They're already classified by language. Okay. And the first thing, since this is an NLP task, the first thing that we're going to do is pre-process our information. And in order to pre-process the data files, we're going to basically extract the name of the file, which is essentially the name of the language, and we're going to extract the different words that are contained in every text file. In this case, one line is equal to one name, right? And so we want to create a loop that can extract the names for us effectively and create a dictionary that maps all of the names that belong to a language to the name of the language. Right? So I invite you to run the next couple of code blocks, right? Now, another pre-processing step that we're going to need over here is to take care of special characters. So if those of you who speak Spanish would know that there are characters, diacritics that Spanish uses, which English does not. And so if for our classification task, having a string, having diacritics that exist in one language but not in the other, especially since we're using Unicode, is going to give us some trouble. So the first thing, at least for this specific use case, is we're going to do a Unicode to ASCII conversion, right? And if all works well, your print statement should convert this last name, which I believe is Lusarski from Polish, without the diacritics, which tell us the stress and the manner of the fricative that starts the word, right? So this unifies, this creates a certain amount of uniformity between the languages, because we don't want our neural network model to be biased. We don't want it to look at diacritics and make a judgment about which language. This is useful, but this will not tell us if our RNN is working well or not. We want to make sure that it recognizes the relationships between different characters, and for that we need some uniformity. Right. Next, we are going to build the dictionary. So we have a list of names per language, and we want to map these lists of names to the language, right? Now, the next two code blocks should do this. And if you run the next print statement, I invite you to test it out for all the different languages that we have in our code here. So I did the test with Russian. You can try Italian. You can try some of the other languages in here. Right. So here's two examples for how you can test your pipeline. All right. You could even test check if your last name, if you have heritage from all of the language groups that are mentioned here, you could check for your own name. All right. Next, we turn the names into tensors, right? So because we are conducting a mathematical model, we want our names, the string of characters, to be represented in a mathematical form so that our model can utilize the information, the relationship between the characters with numbers. Right. So in this case, there are some concepts here. They may have been covered in last week's course, and if not, you can always ask me a little bit more. The first thing we want to do is we want to represent each letter as what's called a one-hot vector. So in this specific case, our ASCII list has a certain number of predetermined characters, right? So the first thing that we did was we used the ASCII listing, right? String.ascii.letters to basically extract every letter. So this is English has 26 plus a certain number of like a certain number of special characters that we have over here. So there's a certain predetermined number. And so in this case, when we say A, which is the first member of the ASCII string list, it's going to have a 1 in the first position and followed by a bunch of zeros. For B, it's the binary is going to be 1 in the second position and everything else is going to be 0. So as you can see, each character in our character list is going to have a unique vector, right? And it's going to have a unique mathematical representation. Now, in this case, a vector is a one-dimensional representation, and for example, a matrix would be a 2D representation. We are going to use tensors, which are a multi-dimensional representation. So just the number of, so we go from just having one column to visualize to 2 columns to basically a thing which a data structure which has more than 2 dimensions in which the data is stored. So in order to create a tensor, and in this case, we are creating one tensor for every character in our list. What we're going to do is use import the torch library, right? And we're going to create just a little function to to create our one-hot encoding, and then convert each line to a tensor. All right. So if you go over the code over here, it's the code's fairly straightforward as far as the wording is concerned. We're using a little for loop to go over things. And once you run them, and I invite you to, in the last 2 lines, the first line where it says print letter to tensor, instead of A, I invite you to try a different letter. Similarly, for the print line to tensor, there's a given last name that we are testing on over here. I invite you to try a different last name and see what dimensions it gives it. This specific tensor for the last name printed over here is the torch size is 10,157. Is it going to be the same if the last name is longer? What if I replace this with Smith? What's going to happen? So I'm going to give you about a minute to maybe test these 2 lines and see if everything works so far. And if it does, then we can proceed to actually coding up our recurrent neural network. Hey, Krishna, thank you for your question. So in order to answer your question, I'm just going to create another little code chunk text box over here and just type things out. All right. So let's say we have a list, and this, let me call it list. And this list has 4 members. So the 4 members are 1, 2, all right. Now, as far as like a Pythonic understanding of what we have over here is concerned, we have some data structure, a list. I shouldn't call this list. And it's got string number 1, string number 2, string number 3, and string number 4, right? Now, one way to represent these different members is we can call our mylist, and we can say member number 0, right? And so if I print this out, it wouldn't work because text code. But essentially, if I did print my list 0, it would give me give me ONE as the output, right? So there is some mapping between the position that a member occupies in a list and the content of the member, right? Now, if I want to basically express all of these members as zeros and ones, right? I don't want to use anything else. I'm only allowed a binary representation. So I am either allowed a 0 or a 1. I immediately notice that if I only use a single unit of representation, then I can only represent 2 of the members in this list. I can't represent all 4 of them. And so a method that we use in specifically in NLP, but it's also used everywhere else, is one-hot encoding, right? And what one-hot means is that there's going to be the number 1 in a vector at one position, and everything else is going to be zeros, right? So if in this case, since my list has 4 members, my vector is going to be, let me just put right? So I need at least 4 positions, 1 position for each member in the list. Now, in order to represent 1 in a one-hot encoding system, I'm going to put a 1 here, and this is going to be followed by zeros. Now, if I want to represent 2, then the position in which 2 is true is going to be 1, and all other positions are going to have the value 0. Now, again, for 3 and 4, if Christopher, you know the answer, I invite you to add it in chat. I want to represent 3 such that the position where the value 3 exists is 1, and everywhere else is the position is 0. So it's just a representation where we use true and false. So does 1 exist? True, you add 1. Does 1 exist over here? It does not, so I add a 0. Does 1 exist in this position? It does not, so I add a 0. Does 1 exist over here? I add a 0, and so on. Okay, so I have another question here. No matter the length of the name I put in, the last number is 57. Okay, yeah, that's a good question, and I will, as we look at the data some more, I'll come back to this. Now, in case you're, 5157, like just consider the output, like it's what is it representing in each of those positions? Yes, Christopher, that's correct. All right, thanks for your question, Dave. Let me know if I don't answer it in the next, like if it doesn't get answered after I explain the training module over here. All right, yeah, okay. Next, we have the, we're going to create the network itself. Now, in this specific case, since we don't need a very complicated architecture, we have a very limited number of input and hidden layers. First, in this case, we use the RNN.module. So RNN is the torch library for coding up a neural network. And so the first thing that we're going to do is we're going to initiate a class and assign it all the values that we will require for coding, right? The actual network design itself is, you can see it somewhere in these 3 lines of code. So first, it takes the input, right? And the input gets passed to a hidden layer. Then the output of the hidden layer gets passed to an output layer, and then we perform a computation on the output layer with the softmax function, and that is the value that we're ultimately going to pass on to the user. Okay, and then the rest of the code here is essentially combining, is just adding the layers together in order to create the recurrent neural network architecture. All right. Now, in order to start, we're going to start with 128 as the number of hidden units, and we're going to use the number of letters that we have as one of the inputs to the neural network. The other input that we're going to use is the number of categories. So in this case, n_category is the number of languages. So we're making sure that our network has the letters, and we're making sure that it has all the available characters, categories, right? Okay. So if you run this code block and the next one, this is just to test if we're able to convert the letter A to a tensor, and if if basically we're able to provide this to the neural network itself along with the input. So in this code block, the input is the tensor for the character A. Next, we have the hidden layer, which is just a zero tensor, where we've got the value 1 at one position, right? Okay. Next, if we want to, after testing it on just a letter, we can go ahead and test it for the last name Jones. And if we do this, it should give us an output, which is just a mathematical representation that comes out after the RNN has finished processing the word Jones. Okay. Next, now that we've set up our RNN architecture, the next thing we want to do is we want to basically prepare our data for training. Right here, the code here has explained how we need a couple of helper functions to make sure that we are correctly interpreting the output of the network. And what we want as the actual output is the likelihood of a given word belonging to a given category. So what we're interested in is if we have 18 possible categories and we have a given word X, which category or which language is the word X most likely to belong to? We're only interested in the most likely candidate. The rest of them are in this specific use case, we won't be looking into them, right? So one second. Right. So here's a little function. In this case, we have the word, we used Jones, and in this specific case, it said German seems to be the most likely category, right? But rather than processing just one word, what we want to do is we want to train our model on all of the thousands of, or at least a portion of the thousands of words that we have at our disposal, because one word is not really training, it's just chance, it could be random chance. So we want our recurrent neural network to be able to learn the relations between a given category and as many members of the category that we can spare from our data set. Right, so in the next helper function over here, it's just we're just creating a training example, and in this case, a training example is a category and a name. So what's the input data? That's the name that we're providing. What's the most likely class category it belongs to? That's the name of a language. So here you've got a bunch of examples of what our training data kind of looks like. Now, once our training data is, we've programmed our training data in the way that we want to, this completes our data processing pipeline, right? So for the NLP task, we started with setting up our data processing pipeline. We also have our the code that we use to set up our neural network. And so the next step is going to be to pass our processed data through the neural network that we have put together. Now, our neural network is essentially going to reduce, as it trains, the difference between a predicted category that a given word potentially belongs to, that the model is generating for us, and the actual category that the language belongs to, that that the word belongs to, that we know from all of the text files that we have, we want to reduce the distance between them, because the better our the lesser um, the lesser number of errors our language model, our RNN makes in predicting a given category for a given word, the more likely it is that the recurrent neural network has been training on the information. Now, as we provide our RNN with more and more information, if we notice that there's no decrease in loss, it just means that the RNN is doing something, but it's certainly not learning from the data that we're providing. And then when when we come to that eventuality, it confronts us with questions about, hey, is our data suitable for this task? Is our model complex or not complex enough? And those are questions that we can answer at that stage. Right now, in this case, we're using for a recurrent neural network, we use the loss function negative log likelihood loss. That's the one that we're using today. Another potential candidate for RNNs as far as loss functions is concerned is the cross entropy loss function, very popular. I don't have enough time to go into them in depth, but essentially picking a loss function for a neural network is usually based on research and the kind of performance that is reported by different researchers when they use recurrent networks. And the negative log likelihood loss and cross entropy loss are good candidates for the kind of tasks that we have set up with our recurrent network today. Now, the second thing that we want to know is the output, just the raw output of our recurrent neural network is just going to be a bunch of, it's just going to be a bunch of likelihoods. But it's not going to tell us which category, like directly tell us which category a given word belongs to. Now, for that, what we want to do is we want to convert the output of our recurrent neural network using a layer. So in this case, we're going to use a softmax layer for this purpose. What a softmax layer does is it takes all the categories that we have available, and it gives us it turns them into the sum of one. So it's essentially going to give us a set series of probabilities. So the closer the number is for a given category, the closer it is to one, the higher its probability, higher the probability is that a given word belongs to that category. So if we have, in this case, we have 18 words, 18 language categories. So we're going to get the sum of probabilities of each of these categories is going to have to be one. The language category which has the highest log softmax output is the one that is going to be printed as the most likely candidate. All right. All right. So let's look at the training loop over here. And Rai, I see your question if about RAG. About now, there is an I personally have read about it, but I have not used it personally. So I don't know if I'm qualified to answer your question. However, I will pass this on to Carlos and Mithun, and we can answer your question some more. I will say that recurrent neural networks are a much are a baby model compared to what we use these days as state of the art. So the architecture overlap may not be so much. Okay, so let's look at the training loop. We created our input and target. We created tensors for our input as well as our target. Then the first thing is, because we need an initial, we need a state that is going to be that information is going to be added to as information as a member of the series is passed on to it. So if you remember our little infographic, And what we need to do for our first member, for the first member of the sequence, we need an initial state. So we just provide a zeroed initial hidden state, right? And then we read each letter in as the input. We keep the hidden state for the next letter, right? Then the final output is compared to the target. So in this case, final output target are both categories. And then there's going to be a back propagation step, which I will cover if I have time, or we might do a different, we might add it to our future workshop series. And then finally, we're going to extract the output and loss from each loop of the training. Output to see what the model is doing, and loss to see if the loss is decreasing, and thus we can determine if our model is training from the information or not. All right. So there's a little bit here about learning rates. Again, it's something that I would love to go into, but like suffice it to say that with recurrent neural networks, one of the risks that we run into is an exploding gradient problem. There's a lot said on it, and I will provide resources for it. And so we don't want our learning rates to be too high. Now, if you run this for loop, it's essentially going to carry out these steps for us. And as you run it, once the function has been set for you, we will go into the next step. Again, here there is the time and math function. It's just to determine how much time our code takes. It's just to give you a rough idea of approximately how long your wait time should be. If your code has any errors or mistakes, it's usually a good time to keep the time library available, so that you don't waste too much of your precious computation time, especially when we are using private enterprises like Google Colab, or any other setup where this time is going to be strictly logged. All right, so let's run the for loop itself. Now, so as soon as it's worked with about 5% of our data, and we see an example output, right? And we can see that the model in the example that it was assessing its performance on, it did not get it right, right? So even with 10% of the data, it still didn't happen, not with 15%. But now, as we move on to about a quarter of the data that we've provided it, we see that maybe things are getting a little bit better. Who knows? Once we are done with this step, once 100% of our data has been processed, in the next step, we will plot the loss function to see what our model was actually doing. At this point, if you are running into any trouble with the code, please let me know. We can troubleshoot if needed. All right, so the code's taken about 1 minute and 47 seconds. So yeah, 2 minutes. Hopefully 2 minutes should be the runtime at which oh no, we took more than 2 minutes this time. Okay, so at this point, let's look at the example outputs that we have over here. Right. We can see that there are some, I think the example generated at the 95% and the example generated at step 1 and step 2, like we see that the character relations might be getting a little bit better. We towards the end than at the beginning. In order to properly assess this, we're going to plot the loss function. Now, according to the and here we as we can see, there seems to be a pretty steep improvement in performance within the first 20% of the data. And even though the decrease in loss is not as steep the rest of the way, we still see that there is some steady amount of decrease in the loss. And what this means is that as we give our model more and more data, it's getting better and better at predicting a category for a given word. And when the predicted category is tested against the actual category, we see that the performance is not bad. And yeah, so at this point, if we saw different shapes in this in this plot, we might take different courses of action. As of now, I'm going to leave this as such. I'm going to leave the model untouched. Finally, we want to evaluate our result. Now, in this case, we want to see how well the network performs on different categories. So the first thing that we're going to do for this is we are going to create what's called a confusion matrix. So in our confusion matrix, we're going to have rows and columns. Now, each actual language that a word belongs to is going to be on the row. And then the language that the network guesses is going to be a column. This confusion matrix is going to use colors as one of the ways in which the likelihood of the predicted language and like the language that the network guesses and the actual language that a word belongs to, their relationship. So if you have any, I'm hoping that the plot also works in terms of darkness and lightness. Please let me know if it's getting hard to read. Now, if you run the next two code chunks, and this is our for loop for creating the actual confusion matrix, and then we want to plot our confusion matrix, right? So just we have the rows over here, we have the columns over here. Now we have a little legend on the right to read this. So the lighter the color of a given square in our plot, the higher the likelihood of there being a relationship between what the model predicted and what was the actual language. Right now, here as it says, the bright spots are where the bright spots over here of the main axis are where the language it guesses was incorrect. And right, so there are some examples over here, and the more of the same color that we see, the more we can determine which language has higher performance and which language has lower performance. Now, finally, like at this point, we've just been working with what's called training data. So we gave our language model data that was in the text files. So it actually was able to view all the data. It had 18 categories. It made up its mind. There's a little bit of test code over here where we're going to work on user input. So if there is a word which may or may not belong to the given training data categories, it's something that we might be able to test. So in this case, we've created a function called predict, where it's taking a word from the user and then it's going to run it through our model. So in this case, we have three last names: Dostoevsky, Jackson, and Satoshi. And as we can see over here, the candidates for Dovesky, the candidates for Dovesky are Russian, Czech, Irish. Interesting. For Jackson, it's English, Scottish, Greek. For Satoshi, the highest probability is for Japanese, followed by Italian and Portuguese. Right. So at one level, this is telling us, giving us information about what these last names, how these last names relate to the language. At another level, it's also kind of telling us something about Russian and Czech and Irish, right? Maybe there is something about S, K, and Y that when they exist next to each other in the context of a person's name, that's something that tells us about how Russian process, how the Russian language creates first and last names. Same for the characters SON. When SON occur next to each other and they occur after a certain set of characters, this tells us something about how the English language processes names, right? Um, Another thing to note over here is if as our language model gets better and better, like something that we know from research, languages that are more closely related to each other, that may have shared history, that have a shared genealogy, may have similarities in how characters are allowed to to sequence with one another in order to create words. So what we started out with our character RNN was just a simple classification model for predicting how a certain string of characters, like if they form a legal word in a given set of 17 languages. What we also created as a byproduct is a recurrent neural network that can also tell us which languages are genealogically related to each other based on the names that people have uh, in those language speaking communities. And broader picture, like sometimes when we work on neural networks, it's important to determine our use case not just in terms of a task that is achievable, but also in terms of broader tasks that can tell us more about language, about communities, about histories. For example, the code over here, there seems to be a little point that was noted that the performance for English, which happens to be a lingua franca, the prediction for English names seems to be poorer than the prediction for Scottish and Greek names. What does this tell us about the file english.txt, right? Do people who speak the English language um, are the names more or less uniform? Now that's something that we can learn by analyzing our data a little more and engaging with our data as much as we engage with the programming of our neural network, right? So just a little NLP aside over there. And as far as other use cases for a character RNN is concerned, we could look, instead of looking at just names, we could just create lists of languages that belong to a word, not just names, and see how our character RNN does for um, common nouns, proper nouns, verbs, adjectives, and such, as opposed to just a small subsection of proper nouns. Similarly, we could create a categorization for first name and the gender of the person. How do first names in Russian allow the same characters to come one after the other as say English? What happens if our gender goes from 2 to 3 to 4? Is our RNN going to be as effective in making this determination? Then we could have character names from different novels and create a character RNN that can tell us about the writer and what kind of choices they make when it comes to picking their characters. Hint, hint, the kind of environment that a writer sets for their stories could determine what kind of characters they choose. Are they writing action adventure for us? Are they writing romantic novels? Are they are they setting their stories in current time in the 19th century? These are all going to tell us. So our character RNN is doing a very simple classification task for us, but it tells us so much about the writer themselves. And if you're an internet, if you're someone who's spent a lot of time on specific subreddits, then you'd know that different subreddits have post titles that are very unique to those subreddits. I don't know, my favorite subreddit is crochet, and like where people post about their crochet projects. The titles look very different from, say, the news subreddit. Right. So these are some of the other simple character level tasks that a recurrent neural network is a good architecture for. And that's all I have for you today. So if there's more that you'd like to know about RNNs, or if there's more terminology, please do drop me a line. I will make sure to get back to you. Or if I can answer it right now, like me, Brenda, and Carlos, we're here to talk some more. Thank you.